Hello, my name is Benjamin Lin, and today I will be teaching you Bent's rule. We will go over the concepts and apply what we learned to some practice problems which are from past Olympiad exams. If you would like to follow along with the guided notes, you can find access to them in the description below. So without further ado, let's just get started. The first thing I want to do is briefly review VSEPR theory and what it predicts. So let's see. The main idea of VSEPR theory is that species with the same charge, such as pairs of electrons, which are all found in a molecule when it makes bonds to other atoms, will repel each other. A molecule will try to keep its electron groups as far apart as possible to minimize the repulsive forces. Therefore, we can predict the geometry of a molecule based on the number of electron domains around the central atom. So hopefully this already sounds very familiar to you. And the idea of VSEPR, it can predict different geometries for a different amount of electron domains. Some people like to call it the steric number, but it's a very similar thing. It's just the amount of groups that are around the molecule. Around the central atom. So we know that when there's two electron domains, we expect a linear shape with a 180-degree bond angle. Trigonal planar, we expect all three of them to lie in the same plane. And 120 degrees apart to maximize the distance from each other. And we could keep going, but yes, there are all of these different predictions, and they all predict some sort of idealized bond angles with each other. Yeah. But with experimental evidence, we can see that VSEPR is not perfect, and we can see deviations from VSEPR everywhere. As a quick and very common example, let's look at all three of these different molecules. All of them have a steric number of 4, right? They all have 4 groups around them, whether they be other atoms or lone pairs, like in this water. So VSEPR predicts that the bond angle for all of these should be 109.5 degrees. However, what's observed is methane, CH4, does actually have a 109.5 degree bond angle, but ammonia, NH3, and water, H2O, have bond angles smaller than that. So now we need a reason to justify, this difference in bond angles from what's predicted by VSEPR. So some people turn to sterics, which is a contributing factor, but does not always give us a reliable answer. So as we see here, sometimes we can use steric effects to justify the experimentally observed deviations from VSEPR theory. And we can try to apply this logic to the deviations discussed in the table above. But here are the two main ideas of the steric argument. One, lone pairs are held closer to the central atom because there's no other nucleus pulling away the electron density. As such, they are closer to the other groups and will repel the other groups more strongly and require more space. And then the next idea is that larger substituents take up more space and have stronger repulsions. So this first bullet point is what really applies to what's going on up here. So we can see in ammonia, we have this one lone pair, and we could say it has extra repulsive force, so it's able to push away the hydrogens with more force, and as such, the bond angle between the hydrogens actually drops from the 109.5 to the 107 degrees. That's what we can use as like part of our steric argument. Then for water, we actually have 2 lone pairs. So these are going to repel each other very strongly, creating a relatively large bond angle, and they will, and they will pinch the hydrogens closer and closer together until their bond angle shrinks to a much smaller angle than 109.5, and experimentally that's observed to be 104.5 degrees. Now, it's your turn. Pause the video and try to rank oxygen difluoride, water, oxygen difluoride, and dimethyl ether in terms of decreasing bond angle, right? So each of these, and try to use the logic that we discussed up here. In this case, they all have the same lone pairs, so this is not really going to be a relevant argument, but this might help you out. All right, hopefully you've paused the video, and my guess is that using this argument, you would argue that dimethyl ether would have the largest bond angle, oxygen difluoride would have the second largest bond angle, and water would have the smallest bond angle. And the reason being is the CH3 groups are relatively big, and they will push each other apart, more so than the relatively smaller fluoride groups, which are, again, larger than the hydrogens, which can push each other apart as well. So that's what we would predict with the steric argument. However, there's more considerations than just sterics. And there's something we have to consider, which is non-ideal hybridization. And really, that's Bent's rule. So Bent's rule is the following. Atomic S character concentrates in orbitals directed toward electropositive substituents. So electropositive groups that are around the central atom. I kind of interpreted this statement to make it a little bit easier to understand. But basically, it's that orbitals involved with bonding to electron withdrawing groups, like electronegative groups, will have less S character. Now, this whole S character thing, might not sound very logical to you just yet, but you'll see exactly what I mean in the next table. So here are the ideal hybridized orbitals. So what we predict with VSEPR theory and the bond angles we should see. So an sp3 orbital that has one s orbital and three p orbitals, that means its S character is 25%, right? 1 out of 4. And the ideal angle is 109.5 degrees. sp2, there's one s orbital and two p orbitals, so 33% s, and then that gives us 120 degrees. sp is going to be 50% s character and 180 degrees bond angle. And if you notice the general trend between s character and bond angle, what do you see? Well, we see more S character corresponds to a larger bond angle. So this is generally the trend, right? So S character increases this way and bond angle increases this way as well. So we can use Bent's rule and apply it to what we see below. Stronger electron withdrawing substituents, like fluoride, will bond to orbitals with less S character, yielding smaller bond angles. Stronger electron donating substituents, like a methyl group, if you know in organic chemistry, methyl groups are electron donating. That's why they can stabilize carbocations. If you're not familiar with this, don't worry about it just yet. Just know that methyl groups, CH3s, are electron donating. So they will bond to orbitals with relatively more S character, yielding larger bond angles. And as we see here, we have the CH3 groups here. These orbitals will have more S character and thus a larger bond angle. And we can see that it's like 111.5 degrees as compared to something like fluoride, which is electron withdrawing. It will have a smaller bond angle because it has less S character in its bonding, and that will give 104.2 degree bond angles. So to answer our question from before, the correct answer was dimethyl ether has a greater bond angle than water, which has a greater bond angle than oxygen difluoride. Clearly, the fluorines are more electron withdrawing than the hydrogen, so that's why we expect its bond angle to actually be smaller than hydrogen, despite the fact that the fluorines are larger groups, and you would expect with a steric argument that it would push each other away more strongly. Now you can try. So compare the bond angles in NH3 and NF3 using just the logic we applied above. So pause the video and try to do that. All right, hopefully you paused the video and thought about it. This problem actually comes from the 2024 USNCO National Exam Part 1, question 52. And it's this first statement right here to evaluate the difference in bond angle between NH3 and NF3. Here is my official solution. It hasn't been published at this time. ACS has not published the annotations yet, but they will be submitted very soon. So here is the thing. I'll just go through the thought process on the side. If you want to read this, you can. Just pause the video and read that. But so for NH3, we have this structure. And for NF3, we have something very similar. So we have this F. Bent's rule tells us that the fluorines, which are more electronegative than the hydrogens, will bond to orbitals with less S character. And because they're bonding to orbitals with less S character, as we observed in the trend up here, less S character means a smaller bond angle. So we would expect that the bond angle of NF3 is actually going to be smaller than the bond angle of NH3, even though we know the fluorine groups are bigger than the hydrogens. And that would actually tell you that this statement is correct because NH3 bond angles are larger than the NF3 bond angles. And then statement 2 you can evaluate separately. Again, that's in the solution right here. There's more to Bent's rule than just the bond angles, however. So here's a problem from the 2013 USNCO National Exam, Part 2, and it's actually question 6. And they ask us to predict the most stable structure of SF3Cl. So immediately, VSEPR theory is going to tell us that the lone pair will occupy an equatorial position to minimize repulsions. We know this because if it's in an axial position, like here, here or here, it's going to have a 90-degree bond angle to the fluorines. It's not technically a bond angle, but you know what I mean. It's going to have a 90-degree bond angle to 3 different substituents. And we know already from the steric argument that we talked about before, lone pairs are going to require more space than other substituents. However, when it's in an equatorial position, like here, it actually only has a 90-degree angle to 2 substituents. So here and here. Just like in this case, it's only here and here. This fluorine down here, if you can visualize that in 3D. So we know immediately that these 2 structures are more favorable than these 2 that are in the beginning. Then, to distinguish between this structure and this structure, we're going to need to use Bent's rule. So there's 2 different ways of thinking about the hybridization of the sulfur. I listed both of them here. One of them is the conventional VSEPR theory way, which is saying that we involve the d orbital in the hybridization, and we have sp3d hybridization around the sulfur. In this case, the equatorial bonds, so here, here, and then this orbital for the lone pair, same thing in that structure, they are formed from the hybridization of the s orbital, the px orbital, and the p sub y orbital. So the p orbital in the x direction and the p orbital in the y direction. So that would look something like this. If we have the sulfur right here, so the s orbital is going to be like that, and then the p sub x orbital is going to be, let's say, coming out of the board and going into the board, and the y orbital is coming out of the board, coming into the board, right? This is the straight up direction here, here. So these all lie in the same plane. Then the axial bonds that follow this straight up and down direction are formed from the p sub z and the d sub z squared orbital. So the p sub z orbital is going to be the p orbital that just points straight up. And the d sub z squared orbital is like this. So we have this orbital here, like this, and then a ring around it. And then the hybridization of these 2 orbitals leads to the axial bonds. Now, the other way of thinking about it, which is favorited by USNCO, is using the 3-center 4-electron bonding model for trigonal bipyramidal species like this. In that case, we consider the central atom to be sp2 hybridized. If you're not familiar with this theory, I recommend you looking it up on your own time, but it's not integral to your understanding of this problem because we can use the other interpretation. Regardless, the way we do it is saying the equatorial bonds, like here, all lying in the same plane. They are formed from the hybridization of the s orbital, the p sub x orbital, and the p sub y orbitals. And then the axial bond is actually formed from the unhybridized pz orbital. So here's pz right here, and then these are the sp2s. So in either case, we notice that the s character is only found inside of the equatorial bonds, right? So here, here, and here. So it doesn't matter which interpretation we use. Bent's rule tells us that the more electropositive atoms prefer to bond in equatorial positions because they prefer orbitals that have more s character. In this case, chlorine is the more electropositive atom when compared to fluorine, so we expect it to occupy an equatorial position. Thus, we know that the last structure is actually the correct answer. So this is the right answer. Let me just clean this up a little bit. So here, the chlorine occupies an equatorial position. So this is the correct answer. In this case, the chlorine is occupying an axial position. And like we just said, this orbital that it's bonded to in this case does not have any s character. So this is unfavorable according to Bent's rule, which states that it's more electropositive, so it should have some s character in its bonding orbitals. So we figured out how to solve this problem from the 2013 USNCO National Exam. And that wraps up our lesson on Bent's rule. If you have any questions, please feel free to ask me them in the comments below. And also, in general, if you have any feedback about how I can improve my videos to make them more understandable or more engaging, just let me know in the comments below. I want to try and improve my content for future reference. And with that, that brings us to the end of our video. Thank you for watching, and happy studying.